Welcome to my presentation about statistics of soft error rate. The target is to understand the statistics, also in terms of mathematics, and the confidence level in the JEDEC JESD89 Annex C.2. Here we see the outline of the presentation. First, I start with a short explanation about what is a soft error and how to determine the soft error rate. Then I will show what the JEDEC standard tells about this. Next, to do some statistics, there are simplified models. I want to talk about Bernoulli distribution, binomial distribution, and Poisson distribution. Then I come to the core of my presentation, which is the confidence interval for one trial. We talk about Bayes' theorem, Euler's gamma function, and the incomplete gamma function. In the standard, the confidence interval is related to the chi-squared distribution. I also will talk about this. And then we go to a less simplified model where the statistics is related to time. In the end, I will check the example of the JESD89A standard. What is a soft error? It is a temporary bit flip of a memory cell in a semiconductor. Usually, this is induced by radioactive radiation like alpha particles or neutrons. You can see in this picture, this is the semiconductor surface, and we have here a N+ well in a P substrate. When an alpha particle enters this substrate, then charges will be made mobile and a funnel is created. There's a drift region and a diffusion region. In a transistor, which is shown on the right-hand side, this particle causes that the conductive transistor could stop conduction or a non-conductive transistor will conduct. As a consequence in the circuit, the memorized bit could change its value. This is called a bit flip. How can the soft error rate be determined? Usually, an experiment is conducted in order to determine the soft error rate, briefly called SER. Structures or certain specific test structures are being radiated for a certain time, and the number of memory cells with changed contents is recorded. So if N is the number of cells, T is the radiation time, and R is the number of cells with changed content, so with a bit flip, then the SER can be determined using this formula, since the SER is assumed to be proportional to the total number of cells and to the time of radiation. A typical unit of the SER is fit per megabit, which is 10 to the power of -9 per hour and per megabit. The JEDEC standard JESD89, and in particular Annex C.2, talks about how to determine the soft error rate plus the according confidence intervals. This was the basis of my presentation because I did not really understand the rationales behind this computation, and in the end I had a big question mark. So I started as written in the standard. My starting point was the sentence, thus we apply the exponential or Poisson distribution assuming the form C1. Here you can see the form C1, and I did a lot of web research, and I did not really come any further using this formula. So I decided to do my own thinking and tried to find out how that works. I want to take you with me to that journey. What was clear to me already is that we need to do statistics. And for doing statistics, we need a certain model as basis. Therefore, I started with the most simplified model I could think of. And this is to use fixed observation time. There's a constant flow of radiation with a constant particle energy. There are identical cells, and all cells are independent of each other. Each cell has a certain probability to be hit by a particle and either keeps its memory or flips its memory, which is a soft error. In addition, I assumed that the probability of a double hit of a cell is negligible. Note that the statistics in the following pages is started from the beginning. That means I try to explain each step one after the other. If something looks too complicated or you do not have the basic knowledge for this, then you can look up this certain things in the web where there are longer explanations than I can provide. I start with one single memory cell. There's a distribution which is called Bernoulli distribution, and this comes into the place when two possible results from a random experiment are visible, either A0 or A1. The names so far are kind of arbitrary, but they have to be linked to certain events. Like if you toss a coin, the head could be A0. You also could define it as 1. Then we have certain probabilities involved. The probability for the random variable being 1 is called P, and the probability for the random variable being 0 is 1 minus P. 1 minus, therefore, because both events together, they are always the case. That means they have 100% probability. The probability mass function from this is defined by, we have either the probability P if k equals 1, where k is the result of the experiment, and Q, which is 1 minus P, if k equals 0. I can show you some graph. So on the right-hand side, we have the possible results, either 0 or 1. And on the y-axis, we have the probability. So if we assume a probability of P equals 0.8, like in the red example, then we see here the 0.8, and the rest is 20% for the 0. Same as the example with the green, where we have 50% probability for 0 and for 1. Now we don't consider a single cell any longer, but a combination of many cells. The combination form a so-called binomial distribution. If we have n as the total number of elements or cells, k as the number of elements with a result 1, and p the probability distribution, same as the Bernoulli distribution, then we have the random variable x, which is the sum of the results from n Bernoulli trials. The probability mass function of the binomial distribution looks like this, with the probability that the sum of the results from n Bernoulli trials is the same as a certain number k, and this is computed by n choose k times p to the power of k times 1 minus p to the power of n minus k. This n choose k is the so-called binomial coefficient and is defined like shown here. This is the factorial of n over the factorial of k over the factorial of n minus k. How do we come to that formula? This is what I want to show in the next slide. Here's an example. We have 7 cells and we want to observe 3 hit cells with a probability of 10% each. That means k is 3, n is 7, and the p, the probability, is 10% or 0.1. The total probability of having 3 cells hit is 10% to the power of 3 times 90% to the power of the remaining 4, multiplied with the number of configurations, how we can come to 3 hit cells. How many configurations are there, or how many possibilities for 3 cells out of 7? I painted here 7 boxes and the 3 cells for which we want to count the number of configurations. Let's start with the blue one, which I distribute to one of the 7 boxes. It could be put to the first, to the second, third, and so on place. Then next, the green cell will be distributed. And for the green cell, since 1 is already covered by the blue cell, 6 open places are possible. That means for 2 cells, we would have 7 times 6 possible configurations. If then the third, the red cell, is placed, there are only 5 empty places. And again, we multiply it with a number to find out the possible configurations. That means we have 7 times 6 times 5 configurations. If we generalize this, then it is n times n minus 1 times n minus 2. And this can be rewritten as the factorial of n divided by the factorial of n minus k. Now, the order of the 3 colored cells isn't important. It's just to make up the mind how many configurations we have. So that means we have to divide by the number of configurations which these 3 cells have. And again, the same applies as before, but now we have 3 empty places with 3 colored boxes. And that means we have 3 times 2 times 1 options to change their order. If this is generalized, this is the factorial of k. Therefore, the number of possible configurations is n factorial over n minus k factorial, and again divided by the k factorial. And this is exactly the definition of the binomial coefficient n choose k. Let's have a look how the graph of the binomial distribution looks like. To be precise, the probability mass function. If you have a look at the blue curve, where the probability is 0.5 and we have n is 20 cells. Then we see here there's a maximum at 10 cells, and when going away from the maximum to the right or to the left, we are approaching 0. Same for the green curve, where p equals 0.7. Here the maximum is more to the right, with the same number of cells as the blue curve. And another example would be the red curve, where we have 40 cells in place, now more than before, and again the probability of 0.5. You see here that the sum of the probabilities for all k here always ends up in 1, because either of these numbers has to be reached in the end. From the shape you see that this could be approximated by the famous normal distribution or Gaussian distribution. But there are some problems. The first problem is that the approximation by the normal distribution is not feasible for rare events. Rare events means we have not many hits. That means the number r is quite close to 0. Which is good if we talk about soft error rate, because it's target to have not many soft errors. The second problem is that for the soft error rate, we have a high number of cells, n, which are investigated. So that could be megabit or even more. And if we have to build the factorial of 1 million, that really can't be used by humans or even not by normal PCs, because the number range is not enough for such high factorials. That means we have to find something which is more feasible for computation. To resolve these issues with the binomial distribution, we approximate it by the Poisson distribution. This is possible if we talk about rare events. The Poisson distribution is the limit of the binomial distribution for large n and small p under the condition that n times p is a constant which we call lambda. Please don't confuse the lambda with a symbol for the soft error rate, which sometimes is also chosen to be lambda. I put here the formula of the binomial distribution, and now we can replace the p here and there by the value lambda over n. This looks like here. The binomial coefficient is replaced by the usual formula. The p is replaced by lambda over n, also here. Since we talk about large n, we can use here the limit for n going towards infinity. In the next step, I put here the lambda to the power of k in front of the equation, and the factorial of k will be put here. Then n factorial over n minus k factorial will be written in a longer form, like here. And in the denominator, n to the power of k comes from this term here. The powers of this term will be split using the power of n and using the power of minus k. In the next step, we can rewrite the equation. This term, lambda to the power of k divided by k factorial, is independent of n, therefore we can put it here. And then we distribute the denominator with the nominator, like visible here. We have n divided by n, n minus 1 divided by n, and so on. These are all in all k terms, so it's the same as we see here above. In the next step, we build the limit for n going to infinity, and you see here n divided by n will for sure go to 1. N minus 1 divided by n also will go to 1, since n is a big number. K is limited, therefore also this term will go to 1. So all of that will be replaced by 1. This term, since n will go towards infinity, here is remaining 1, and 1 to the power of minus k remains 1, so also this term drops. And this term is a little bit special, because in the denominator we see n will go to infinity, and also the power here will go to infinity. And there is a solution which is the exponential of minus lambda. I rewrite the limit here, and due to our simplifications, the remaining term is lambda to the power of k divided by factorial k times the exponential of minus lambda. So this is a quite small equation, and we see we have only one parameter, which is lambda, for the Poisson distribution, sometimes written as Poisson of lambda. K is the parameter, it's the value for which the probability has to be determined. Following our assumptions, the soft error rate is Poisson distributed, since usually we talk about rare events, that means only a low number of bit flips. Here's an example of different Poisson distributions. The parameter for the orange curve is 1, lambda is 1, and you see here the probability for having 0 bit flips is the same as having for 1, and then it will reduce pretty much until higher values of k. If we use that example for lambda equals 4, we see there is a peak close to 4, and also here for higher values of k, the probability will decrease. Another example is lambda equals 10, and here you could already imagine that a approximation of a normal distribution would make sense. But our intention is to approximate the binomial distribution for low values of bit flips. That means usually small values of lambda. So now let's come back to our main question, which is about the confidence interval if we have just one trial available. We know that the Poisson distribution is a good approximation for soft error rate, but we don't know the parameter lambda so far. Lambda needs to be determined. We want to find out the probable range for lambda when the result of one trial only is known. So let's make a thought experiment. We start with all possible Poisson distributions with the same probability for lambda and do one trial per Poisson distribution. In graphical terms, this looks like shown here. First we start, of course, and then we assume different distributions, different Poisson distributions with the parameter lambda set to different values. So we start with lambda equals 0, lambda equals 1, and so on. Then, from each of these distributions, we do one experiment. We draw one result, R. R is the number of bit flips, and R could be 0, 1, and so on. Same is done for the next Poisson distribution, lambda 1. We also do one experiment. The problem here is that we do not know the lambda, but we will know the R. In this tree, conditional probabilities are involved. For example, the probability that R equals 1 under the condition that lambda equals 1. This is R equals 1 under the condition that lambda equals 1. The vertical line here means under the condition or given. Since R is assumed to be known by experiment and lambda unknown, we need to somehow invert the graph to find in the end the value for lambda. A good tool is Bayes' theorem. We have the same probability tree as shown here in a simplified version, with a certain probability for an event A and the inverse probability, so 1 minus the probability, for the event A bar, which is the inverse of event A. Then, after the first experiment, a second experiment is done under the condition that the first one, event A, occurred. Then we come here to B, or the inverse result B bar. On the right hand side you will see the probability that A occurs and B occurs. And here we have the conditional probability P index A of B, which is the same as shown before, the probability for B under the condition of A. Now, since we have this graph available, we ask ourselves, what is the conditional probability P of A given B? So we need to somehow invert this graph. And this is the result we want to get for lambda, shown in the example with the SER before. To explain how the Bayes theorem is derived, I have here 2 times the probability tree. Here we start with A and then we do B. Here we start with B and after that we do A. There are 2 ways to come to the probability for A and at the same time B. First we go the P of A times the conditional probability P of B given A. The second way to have both results is here to go this way, probability of B times the conditional probability of A given B. This is written down here. And if we omit the center term, then we get an equation. This is the equation for the probability of A given B. Is this one. We divide by P of B, put it here, and in the end we get PB given A times P of A divided by P of B. This sounds nice, but the problem now is that P of B is not yet known. So what about P of B? If we look at the chart, we see one way here and here to do determine P of B, and the other way going over A bar and also going here to B. That means we can combine both paths. The first P of A times P of B given A is this path, and P of A bar times P of B given A bar is this path. We combine it and we come to P of B. In the next step, we replace the denominator P of B in the previous equation and simply rewrite here and get the term P of A given B, which will come from P of B given A. So we kind of inverse the probabilities, the conditional probabilities, using Bayes' theorem. So now let's see how we do this for our problem with the Poisson distributions. With Bayes' theorem in mind, we go back to our confidence interval for one trial. You remember that chart, I guess. So what we know is that the conditional probability for R given a certain lambda is according to a Poisson distribution. This is that path here or here. Then we also know from Bayes' theorem that P of lambda given R is the same as P of R given lambda times P of lambda divided by P of R. That gives us a way to somehow invert this graph. Now what is still missing is the P of lambda. Since we know nothing about how the lambdas are distributed, I assume an equal distribution with a uniform probability. P of lambda is 1 divided by L. L is a so far unknown maximum number. From this, I can determine the denominator P of R. Using the approach from before, we go over each of the paths. That means P of R is the sum of all P of lambda times P of R given lambda, using all possible paths here for one distinct R. In formula, this is written with a sum symbol. We start from lambda equals 0 till lambda equals L minus 1. We assumed the uniform probability P of lambda is 1 over L. And we use here for the PR given lambda the Poisson distribution. In the chart for clarification, I used integer value of lambda. But in reality, we cannot claim that lambda is an integer value because it's a parameter of the Poisson distribution. Therefore, we want to go to continuous lambda, and we also want to go for infinite values of L, since lambda in reality could be any value, any positive value. So using this approach, going to continuous lambda means 1 divided by L will be a differential lambda, and the discrete probability mass function will become a continuous probability density function. That means the probability that the result will be between lambda and lambda plus d lambda is the same as the probability for R given lambda times the differential d lambda. That means the sum from the equation one page before will now go to be an integral. We build the limit for L going to infinity of this sum from the page before, and 1 divided by L will be the d lambda. The rest remains unchanged, and the sum will go to an integral, and since we choose L to go towards infinity, this integral has the upper boundary infinity. This looks nice, but this is not something which we usually solve. It's not straightforward maths, and the question is how to solve this integral. This we will approach in the next slide. To solve this integral, we need to have a look at Euler's gamma function. There's a definition. Gamma of n plus 1 is the integral from 0 to infinity t to the power of n exponential of minus t dt. There's an interesting property of this function, and we do the integration by parts. So I simply rewrite here the integral, and we do the integration by parts. If we use first this one the same, and we integrate the right-hand side of the integral of the product, then we come to t to the power of n times minus exponential of minus t, which is the integral of that, both at the same boundaries as here. And then we subtract the integral of the derivative of the first, which is n times t to the power of n minus 1. And again, we have the integral of the right-hand side of the product. We integrate, same limits as before. And in the next step, we evaluate this using t going to infinity. And in this product, the exponential wins, and all of the stuff will go to 0 if we put t as infinity. If we put t as 0, that means this here, 0 to the power of n is always 0, and again we come here to a 0. Then we have a look at this integral. Since we integrate over t, we can put the n in front of the integral. We also can put in minus 1 here, combine it with this minus, and we get the plus. The rest here is unchanged, but now we see, having a look at this initial equation, that if we use n minus 1 here, n minus 1, we get the same as above. That means gamma of n is the same as here using n minus 1, and that means we get n times gamma of n. This is an interesting property, because if we write here, gamma n plus 1 is the same as n gamma of n. This was an induction equation, and now we want to find out where this induction begins. I tried to compute a simple value for gamma where n equals 1. Then we have here in the power of t a 0, which is n minus 1, so 1 minus 1 is 0. The rest remains unchanged, and since t to the power of 0 equals 1, I simply have to integrate the exponential of minus t, which is minus the exponential of minus t, using those limits. If we put infinity to the t, then the rest is 0. And if we put 0 to the t here, exponential of 0 equals 1, and we get here this term, and minus times minus is 1, so means the gamma of 1 is 1. This is the equation from the previous slide, this induction equation. And if I start with gamma of 1 equals 1, I can conclude that the gamma of n plus 1 is the same as the factorial of gamma of n. So that means the gamma function is a generalization of the factorial to non-natural numbers, because n is never claimed to be a natural number. What we learned now for Euler's gamma function, we will use in our problem with a confidence interval. So we ended previously that we wanted to determine P of r, which was this integral. With the knowledge from the gamma function, which is defined here again, we can conclude that this term in the denominator can go in front of the integral since it's independent of the integration variable lambda. Then we compare the lambda can be replaced by the t here, and the r is replaced by the n. So you see P of r is the same as 1 over r factorial times gamma of r plus 1. Gamma of r plus 1 is the same as r factorial as we had in the slide before. That means the probability of r equals 1. Originally we wanted to have P of lambda given r, and we know that if we go for infinite small lambda, we had this equation. We learned now that P of r equals 1, so we can omit it from the equation. And we define the probability density function P of lambda given r, which is now a little bit differently defined than this one, because this is a continuous distribution. And this continuous distribution is defined by the limit of that probability divided by d lambda, and the limit has to go to infinite small lambda. That means if I use that equation and divide by d lambda, I get almost this one, and the remaining term is P of r given lambda. In the end, P of lambda given r is the same as P of r given lambda, and this P of r given lambda we know already we have from the Poisson distribution. As a side note, you could conclude that P of lambda given r is the same as P of r given lambda, which in fact is the case for our example, but in general this will not hold. R is discrete and lambda is continuous. R is the number of flipped bits after an experiment. This never can be a continuous number, but the parameter of the Poisson distribution lambda is a continuous value. What can we do with this result now? So let's assume that we got the result 2 from one trial. That means we have 2 bit flips after one measurement after a certain time. The task now is to find the values for lambda with the most likely 80%. I will put here the figure of a probability density function. This is created from the formula from the previous slide. You see here, that's the probability density function. That means it's continuous now. On the right-hand side, or on the x-axis, we have the values of lambda. Here we have the probability densities. We assume that r equals 2, and we get a curve which looks like this. The maximum here is for 2, and now we have to find a way to getting the most likely 80%. What we could do, we could an area which is 80% of the total area, and then we assume that this is the most likely 80%. For such questions involving the area under a graph of a probability density function, we use the CDF, which is the cumulative distribution function. I define this as fr of lambda, and this is the integral of pr of u, integrate over the variable u from 0 to lambda. So that's simply a running integral, and pr of u in the graph before was the same as u to the power of r divided by r factorial times exponential of minus u. We can again bring the r factorial in front of the integral because it's independent of u, and we end up with this equation. This looks pretty much like the gamma function, but the integration limit is not infinity, it is a distinct value lambda. For a non-infinite integration limit, also here functions are defined. We have the lower incomplete gamma function, now defined with the upper integration limit x, which is a parameter. The symbol is a small gamma, and there's a regularized lower incomplete gamma function, where this lower incomplete gamma function is divided by Euler's gamma function with the same parameter n plus 1. And the symbol for this regularized lower incomplete gamma function is a capital P. Using this, we can solve the problem from the previous equation, which is here again. And you see here already, if we compare, the upper integration limit is here lambda and here x. That means the x will be replaced by a lambda, and the value of n here is a r here. U, by the way, is replaced by the t. No change outside with the parameters. And that means all in all, we will get the regularized lower incomplete gamma function with the first parameter r plus 1 and the second parameter lambda. How does this look in graphical terms? I put here some graphs for the CDF, which is the cumulative distribution function, for the parameter lambda. Lambda is here, dependent on the result r, and r now is for the green curve 0, for the red curve is 1, and so on. And here I have 5 for this yellow. What we see, of course, that the cumulative distribution function will have its saturation at the probability of 1. And now the question is to find for 80% confidence interval, let's say for the red curve, which is the value here, for 10%, and for 90%, which is the value here. 80% confidence means lying between 10 and 90%. Therefore, the crossing points of the red curve with a 10% line here gives the lower confidence limit, and the 90% crossing here gives the upper confidence limit for 80% total confidence. The same occurs for other parameters of R, like R0 or R2 and so on for the other curves. So as an example, if we talk about this 10% limit, then we want to find a value for a lambda where 10% equals P of R plus 1 lambda. This is done by the inverse function P inverse, written here indicated with a -1. And since we need a value for lambda, we need to find the inverse function for the second parameter lambda. We write it in this way: P inverse of R plus 1 and 10% equals lambda. For a confidence level which is not 80%, but in general 1 minus alpha, the lower limit is alpha half and the upper limit is 1 minus alpha half. So for example, if we talk about 60% confidence level, alpha is 40% and the lower limit is 20% and the upper limit is 80%. So then we can generalize this equation to get the confidence interval for a confidence level 1 minus alpha. The interval means lambda has to be between those two limits. The lower limit is the inverse P of R plus 1 alpha half, and the upper limit is the inverse of P of R plus 1 and 1 minus alpha half. This basically is the confidence interval which we wanted to find. So I was quite happy to have it found, but there's still some problem that in the standard this P function was not used. I had to find out how this is linked with that P function. The standard JEDEC used the confidence interval related to a chi-squared distribution. Why does this standard JESD89 include the chi-squared? From historic point of view, the tables for the inverse function of P were not available, but for chi-squared they were available. This is the probability density function of the chi-squared distribution, with n being the so-called degree of freedom. And if we compare this probability density function with what we wanted to have, This is the equation from the previous slides. We see a certain similarity. There's an exponential term also here, with x taking the role of lambda, similar. We have that lambda here, which corresponds to that x. And we have here the gamma function, and here the factorial, which is also, let's say, quite similar. So I did a trial, and in that fn of x, I replaced x going to 2 lambda, such that the exponential function here is identical, and I replaced n by 2 times r plus 1, such that here it looks similar. So in the next slide we do the calculation more in detail. This is the chi-squared distribution, and I wanted to replace these values. First of all, I also have to replace the index here with n going to 2 times r plus 1, and the value of x is replaced by 2 times lambda. Now the n is replaced like here. Again, the n is replaced like here. X is replaced by 2 lambda. The n is also replaced. And again, x is replaced by 2 lambda. Now I simplify in the next step. That means on the right hand side, the 2 times and the divided by 2 will cancel. Here also. Here also. And the r plus 1 minus 1 will end up in simply r. The exponential here will be minus lambda. And the next step of simplification, I rewrite the exponential here with a e function, which is not really simplification, it's rewritten. Then the 2 to the power of r will cancel with here in the denominator, but 1, 2 from the plus 1 is missing. It ends up here. And the gamma function of r plus 1 can be rewritten as r factorial. As a preliminary conclusion, we can say that PR of lambda is the same as 2 times f2 r plus 1 of 2 lambda. I put the 2 times in front because here it's in the denominator 1 additional 2. From the probability density function, we now go to the cumulative density function. So we integrate with the du now. And we do a substitution with a variable v, which is 2 times u. That means I put here v. Here. The du then will be half of dv. And the upper limit lambda, where u equals lambda, will go to v equals 2 lambda. The lower one, 0, is not changed because 2 times 0 remains 0. In the next step, the 1/2 and the 2 will cancel out, and we end up with that simplified version. If we now use a capital F as a symbol for the CDF of the chi-squared distribution, we have as an upper parameter the 2 times lambda, we have in the index 2 times r plus 1. Now we do the same exercise as before. We search a lambda for a specific value of p of this cumulative probability function. This looks like this. And we then use the inverse function. That means 2 lambda remains at that side of the equation, and the inverse function will be used for the value p here. And if we solve this for lambda, we find lambda is half of this inverse function. If we want to replace the value of p with a certain confidence level, 1 minus alpha, then as before, the lower limit is half of alpha, the upper limit is 1 minus half of alpha. And now we can use the whole interval. The lower interval boundary is the inverse of the chi-squared function, cumulative chi-squared function, then the half of alpha half. And the upper limit, we use the same, but as a parameter 1 minus alpha half. Since f minus 1 is the inverse function of the CDF of the chi-squared distribution, it is sometimes denoted as chi-squared with a parameter p and k is this. So it's simply rewritten to a kind of usual notation. And then we rewrite lambda is element of that interval, and we rewrite this here. So that means p is here alpha half, and p here is 1 minus alpha half. This is an often seen convention, but you need to take care. There are obviously 2 definitions for the chi-squared function. One relates to the so-called low part and one relates to the upper part. And the upper part is 1 minus the lower part. And then you have to replace p by 1 minus p. Unfortunately, the nomenclature is not always the same and it's not strictly defined. Also, you need to take care if you use tables of the chi-squared distributive function, then you need to take care which one really to be used. To finally come to the equation of the standard, JESD89, we now go to a less simplified model where we relate the statistics to the time of measurement. That means the assumption of fixed observation time is now dropped. We can have processes which depend on time, like the soft error rate, and this depends on the time of exposure to radiation. The parameter lambda of the Poisson distribution is not a fixed value, but for SER it is time dependent. We can reasonably assume an effect which is proportional to the time t. That means if we have double the time of radiation, we assume that lambda is doubled. In general, lambda is then defined by a rate times the radiation time, and the rate r has a unit of 1 per second or 1 per hour. The effect of the soft error rate depends also proportionally on the number of investigated cells. That means if you investigate double the amount of cells, then the SAR effect will also double. That means the rate is a SAR number times the number of cells. All in all, we can say that lambda equals the SAR times n times t. We solve this for the soft error rate. That means soft error rate equals lambda divided by nt. Don't confuse this lambda. Here, this is the parameter for the Poisson distribution. Sometimes the soft error rate also has a symbol lambda. We use this lambda, which we had from the confidence interval, and we simply divide the lambda by nt to get the confidence interval for the soft error rate. This is now finally the formula C3 of the JESD89, where the upper part of the chi-squared is used. On the lower part of the slide, you see the quotation from the standard, which is a screenshot. It's written a little bit different than in our formula here. That means it's written as lower limit chi-squared 1 minus alpha half and k. So you see here the 1 minus alpha half. It's here on the upper boundary because here the upper part of chi-squared is used. And we divide here by 2 times n times tr. Tr is the time of radiation, which is the same as t here. And what they also do, they put here a 10 to the power of 9. This has the reason that the unit of fit is used, which is 10 to the 9 hours. There's also an annotation that k is the number of degrees of freedom, and k equals 2 times r plus 1. This is the same as we had here. Finally, my effort brought us to the same equation which is given in the standard, and I was very happy about that. In the end, I wanted to evaluate the example of the JESD89. There's a table C3 with examples. There were always used number of devices, 3,500. After a certain time, in hours, like here 150 hours, one error occurred. That means one bit flip occurred. And from this, the component SER can be computed quite easily. The difficult thing, as mentioned, was the confidence level. I wanted to confirm the example in the JEDEC standard, particularly in table C3, and I used this code of Mathematica. Instead of looking up the numbers in the chi-squared tables, Mathematica is my favorite tool doing mathematics. And here is the code given. Since not all of you are used to Mathematica, I'll explain a little bit what happens here. The 3,500 is the constant number of memory cells given in the example. Here are the number of errors after time. So I assumed 0 error after 149 hours, 1 after 150, and so on, according to the table given in the standard. Then I used different values for alpha. Alpha is 1 minus the confidence level. That means the confidence level was 90%, 80%, and 60%. I multiplied the whole result with 10 to the power of 9. This is because the unit in the end is fit. And in the next line here, I did a formatting of the table, and I used certain table headings. So this is the table of the standard as a result with the confidence level here. And this is the result of my mathematical code. Look here that the levels is kind of inverse because of the different chi-squared table. So that means you need to bring the 5% column together with a 95% column. The numbers itself are pretty much the same. On my result, there are more decimals than here. But I was very happy to find identical numbers with my computation and with that example. Maybe you remember when I started my presentation, I said I start with my research with this sentence from the standard, which was, thus we apply the exponential or Poisson distribution assuming this form. And this turned out to be really a bad way. I didn't come further, so forget about this sentence in the standard. In the end, I found a way to show the results of the standard, and I think I found out what is the reasoning behind this standard. I have to admit that in my presentation there was a lot of math behind and a lot of statistics behind. So if this was too mathematical, then I found out that there's a quite nice YouTube video about soft error rate. It's nothing about statistics, but it's about the history of cosmic radiation and the effect of cosmic radiation on our lives. With that, I thank you for listening. I hope you learned a lot, as I did during my research, and wish you a nice day. Goodbye.